Okay, so with this set, we've already seen how you would compute the total number of subsets, how you would compute the number of subsets with a specific number of elements in them, and how you would compute the number of subsets that have a specific element. For example, we did how many of them have just 2. We've done how many of them have 2 and 3. So the only thing really left to look at with this set is how many subsets have 2 or 3. In this case, or is going to be different than what we did when we said and. And implied it had to have both 2 and 3. It couldn't have just one of them. Or means exactly that. It can have just 2 or just 3 or just both of them. So because this is a very small set, I am going to write out every single subset so you can see what the answer is going to look like. So here we have every single subset of our set A. And what do we need to look at? Well, we need to look for every subset that has 2 or 3, or of course that would include 2 and 3. So we notice that this set has a 2, this set has a 3, this set has a 2, this set has a 3, this set has a 2 and a 3. The or includes both of them, or one of them. This has both. And, or a better way of saying it, the or basically means it has to have at least one of these two. And this has both, so it definitely meets the criteria of having at least one of those two. And similarly here, this set also contains at least 2 or 3. So what do we find? Well, the number of subsets that have 2 or 3 is going to be 1, 2, 3, 4, 5, 6. The answer we're going to be looking for is going to be 6. But how are you going to compute this for much larger sets where you can't reasonably write out all of the subsets? Well, we're going to do this with 2 methods. We're going to do this with our 2 to the power of n method, and we're going to do this with the n choose k method. I prefer this method, but I think this method is going to be much quicker. Okay, so before I use one of the methods, let's visualize this problem a little better. Let's say you have all of the subsets A in here. We have all 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. Each of these dots is going to represent one of those 8 sets. And we want to find the sets that have, of course, 2 or 3. I'm going to mark the sets that have 2 with blue, and the sets that have 3 with red. So we can say, of course, we had a set that had 2, the set 2, a set that had 1 and 2, so that had 2. We had a set that had 3. We had a set that had 1 and 3. We had a set that had we had a set 2, 3, which had 2, and it had 3. We then also had the set that had all of them, 1, 2, 3, which had obviously the 2, and it had the 3. So when we're counting this, a good way to visualize how we're going to do this, you can say the answer is simply going to be the total number of dots, all of these green dots, minus just these 2 dots, right? There's 6 things here. 1, 2, 3, 4, 5, 6. So a really good way of figuring this out is saying, hey, the total is 8. We know there's this many, so why don't we just subtract what doesn't fit the criteria, because that seems to be easier here. So in this case, it would be easier to compute the total number of subsets minus these sets right here that do not meet the criteria we're looking for. And that's the technique we're going to use for our 2 to the power of n method. I've actually decided I'm going to keep this up here for visual purposes and just do the 2 to the power of n method. So we know 2 to the power of n can be used to compute the total number of subsets, and that's going to be when n is going to equal to the number of elements in our set A. So we know the total number is going to be 2 to the power of 3, which is going to be 8. Okay, but let's say we want to subtract what we don't want. So this is going to be our total. Let me rewrite this a little bit nicer. Okay, so we know our goal is going to be to say that the total minus what we don't want is going to equal it's going to equal just the answer, right? Intuitively, I'm just going to write that. I don't want to write down a longer sentence here. That's what we're going to look for. So what we need to do is we need to find this number and this number. We know the total is going to be 2 to the power of 3 from the video where we explained why that is. It's going to be 2 to the power of n, where n is going to be the number of elements that A has, or the number of free elements. That's going to be our total. Minus. Now, how do we figure out what we don't want? Well, what we're looking for is we're looking for the number of subsets that do not have a 2 or a 3, which means they have neither a 2, neither a 3. Not a 2 and not a 3. Well, the only sets that would have that would be, of course, mentally speaking, the empty set, which has neither a 2 or a 3 and a 3, and of course, the set containing only 1. But how would you think about this? Well, you say, okay, we don't want to have a 1, so we can put a cross over here. And then we ask ourselves, okay, well, if that's what we're looking to compute, let's forget about these elements I'm going to circle. So that means what we're really wanting to compute is how many sets have a 1 in them, just a 1. And that's going to be like saying, imagine 2 to the power of n is equal to 2 to the power of 1, because we only have one element here that we don't want. We don't want all of the sets, all of the subsets that have this. So at the end of the day, what we're computing is going to be 8 minus 2, which is going to be 6, which is exactly the answer we got beforehand. Now we're going to try and compute this using the method n choose k. Now, the way we're going to use this method is going to be a little different. Instead of looking for taking the total, this big circle, and subtracting from it these 2 dots, we're instead going to focus on what we've actually circled to fit our criteria here. And what do we notice? Well, we notice that we have 2 sets here. Well, no, here's a better way of thinking about it. We notice that we have 3 sets that are going to have, there are 4 sets that have a 2, and there are 4 sets that have a 3. So maybe we can just count, well, how many sets have 3, how many sets have 2, and add them together. That makes sense, right? We're looking for all the blues, and we're looking for all the reds, so just add them together. But the problem is, some sets have both 2 and 3. And if we add all of the blue and all of the red, we're going to end up with counting these 2 subsets twice, which we don't need to do. That makes no sense. If the answer is going to be clearly 6, and we count these sets twice, our answer is going to be 4 plus 4, because we have 4 blue and 4 red, and we're going to get 8. We're going to overcount them because we're going to count these sets twice. So what are we going to do? We're going to subtract the set that contains both of them once, because that seems to make logical sense, right? Count how many of them have 2 once, and count how many of them have 3, and then subtract the ones that have both of them. So what is that going to look like? Well, first, let's compute how many sets have only a 2. That's going to be like saying, up here, let me get rid of all of this notation from the previous half of the video. That is going to be the same as saying, well, let's fix the 2 and then ask ourselves, okay, since the 2 is here, we're just going to ask ourselves, what can we add to this set in order to keep it fitting the criteria of having only the 2, only the blue? Well, we're going to say we can only choose from 2 remaining free variables, 1 and 3, and we can either choose none of them, we can just leave this as the set containing 2, or we can choose out of the 2, one of the 2. We can say this is a 1 or this is going to be a 3, and both of those sets are going to contain 2. Or we can say it's going to be 2, choose 2. It's going to be choosing both of them. It's going to be 2, 1, and 3, right? This is going to be all of the sets containing 2. Okay, now let's do our next half. Next, we're going to compute all of the sets containing only 3. So, what is that going to look like? Well, that's going to look very similar to what we've done with 2, right? We're just going to fix the 3 instead this time. And we're going to say, well, this is the same as saying 2, choose nothing, right? Because we're just going to say, imagine a set with 3. You can add nothing to the set, and it would still fit the criteria of only containing 3. Or you can say, out of the 2 options, 1 and 2, you can choose one of them and add it to this set, like this, or like this, right? We're choosing one of the 2 options we have left. Or you can choose all of the options, which is going to be 2, choose 2, so you can just add a 1 here. Okay, and I think you can kind of already see what I'm talking about with us double counting some of these sets. So this is going to be the subsets containing only 3. Now, let me better have you visualize why we need to subtract this. Okay, so we have 2 sets. We have everything in this black circle. Every dot is going to be a subset that's going to contain our 3. Then we're going to have the green circle be all of the subsets containing 2. Now notice, when we count this, we're going to want to count everything in 3 and everything in 2. But because we have this overlapping area here, we're going to want to subtract it once, because when we subtract it once, it's going to say, okay, let's count all of the sets containing 3, add all of the sets containing 2, but let's just subtract from the sets containing 2 the ones where they contain 3 as well. So we're just going to subtract this area that overlaps once, because that way one of the circles stays whole, and it'll be like saying this, right? It'll be like having this whole circle plus this little circle with a bite taken out of it. That's really what we're doing when we subtract it, is we no longer have this area overlap and double count the sets. We're instead just going to say, okay, these sets are going to belong to the 3, and we're just going to count the others for the 2. So that's what we're going to do here. So our answer is going to be these 2 minus, so this is going to be a different thing, so we're going to say, we'll just label this 3, we'll label this up here as 2, these are just going to be labels, and then this is going to be minus, so because we're looking for sets containing both of them, we want to fix both of these variables, which means we only have one choice. So when you have a set like 2 and 3, you have the choice of adding nothing to it out of your available options. We have one available option, and we're going to add nothing. So this is just going to be leaving it like this. Or we can add that one available option to it, right? We can just add it like this, and there's how many ways can we do each of these options? So we're going to add these 2 and subtract from that sum this bottom number down here. So let's quickly compute both of these. So let's compute how many subsets contain 2. 2 choose 0 is going to be 1. There's only one way you can choose nothing. 2 choose 2 is going to be 2 factorial over 1 multiplied by 2 minus 1 factorial. This is 1. This is going to be 1. 2 factorial is 2 times 1 over 1 is just going to be 2. So this is in fact just going to be 2 plus 2 choose 2 is going to be 2 factorial over 2 factorial multiplied by 2 minus 2, which is just going to be 0 factorial. So this is just going to equal to 1. 2 times 1, and then this up here is going to be 2 times 1. 2 times 1 over 2 times 1 is going to be 1. There's only one way to choose 2. So it's going to be plus 1. It's identical. These are the exact same options for having the sets only containing 3. So we're going to say there are 4 subsets containing 2. There are 4 subsets containing 3. How many subsets contain both of them? Well, 1 choose 0 is going to be 1. 1 choose 1 is going to be 1, so there's 2. So our answer is going to be 4 plus 4 minus 2, which is in fact going to be 6, the answer we're looking for. The number of sets containing only 2, only 3, and then both. So this is how you would solve this problem using both of the methods. For slightly more complicated situations, you're going to find yourself with larger sets.